This program, PZ, allows you to relate three key aspects of a system: the pole zero plot, the impulse response, and the magnitude and phase of the DTFT. To start, let's specify the system by means of two vectors, b and a, which are respectively the coefficients of the numerator and denominator polynomials of h of z, expressed in powers of z to the minus 1. So here, let's do a simple FIR system. The pole zero plot comprises two zeros on the unit circle and a pair of poles at the origin. Here is the impulse response, and here are the magnitude and phase of the DTFT. We can change the frequency limits of the plots with these controls here, and we can interrogate values of the magnitude and phase as a function of frequency by clicking into either plot and moving the cursor. In addition, we can express magnitude on a dB scale with this control here. Now, in addition to being able to characterize the system in terms of the b and a vectors, we can also express the vectors in terms of zeros and poles, either in rectangular coordinates or in polar coordinates here. When a system is described in terms of its poles and zeros, it's only to within a multiplicative constant k, which you can specify here. So if we change this to 2, h of n will change as well. One final thing that needs to be specified is the region of convergence. For an FIR system, region of convergence is the entire z-plane, so it's grayed out here. You can also specify the system interactively by moving poles and zeros directly on the z-plane. For example, let's modify our pole zero plot by picking up one of the poles and moving it. By default, singularities will move in complex conjugate pairs. This is now an IIR system whose region of convergence is shown in the cyan-shaded region. And as you can see, the magnitude and phase and the impulse response have been automatically updated. You can remove a singularity by shift-clicking it. Now you can also add singularities to the z-plane by dragging them from this little dock here. So let's add a pole. When poles are on the real axis, or on the imaginary axis, or on the unit circle, you're going to see little boxes show up which tells you that you've reached your destination. After you've dropped a singularity on the z-plane, you can reposition it by hitting Enter on the keyboard. Now you can use the arrow keys on your keyboard to move it either axially or radially. If you hold down the Shift key, you'll move it in larger increments. Hit the Enter key again to drop the singularity back on the z-plane. Now, when poles and zeros overlap, they cancel. Now, if you don't like any of the changes you made interactively to the pole zero plot, you can use Ctrl-Z to reverse them, or Ctrl-Y to bring them back. Now let's add one more pole to this system. Let's add it at 1.5 on the real axis. The region of convergence is determined by the value in this box here. It's a single value that lies within the region of convergence. Here, the value of inf specifies that this is a right-sided system, since the region of convergence extends from the outermost pole to infinity. This is an unstable system. The impulse response is monotonically increasing, and since it's unstable, nothing is shown for the magnitude or phase of the DTFT. We can change the region of convergence by putting another value in the box here, for example, 0. This is now an unstable left-sided system, and the magnitude and phase are again not shown. You can also set the ROC by right-clicking directly in the z-plane at a point which you would like to include in the ROC. For example, here it's right-sided, here it's left-sided, here it's two-sided but unstable, And finally here, it's two-sided and stable since the region of convergence includes the unit circle. In order to show some other features of this program, let's go ahead and clear everything out and start again. Now you can also specify this system using just about any legal MATLAB expression. Let's go ahead and specify a Kaiser filter. A nice 14th order filter. Show it on a dB scale. You can change the bottom limit if you like. And now the cursor expresses magnitude in dB. Now we can get a sound from a sound file. Let's get seashell. Play it.
She sells seashells.
And filter it.
She sells seashells.
Now you can use this program to show graphically the relation between the pole zero plot and the magnitude of the DTFT. To do that, let's clear things out. Set things back to magnitude. And let's put a single zero at 0.5 and a single pole at minus 0.5. Now let's go over here and click this box which says bug. A small green dot, which I call a bug, shows up here on the unit circle. The bug is constrained to run around the unit circle, and its position is given by the angle, which is determined by this cursor. So right here, the bug has an angle of about 0.5 pi. You can also change the angle with this slider or by setting the value in this box here. Now in Chapter 5 of the book, we show that at any angle omega, the value of the magnitude of h of omega can be determined as the ratio of the length of a line drawn from the zero to the bug divided by the length of a line drawn from the pole to the bug. In this case, they're both equal, so at 0.5 pi, the magnitude is 1. Similarly, the phase is the difference in the angle here minus the angle here. It's a positive angle shown there. Finally, you can show the respective contributions of the pole and the zero to h of omega using this control here. Right now we're showing h of omega. This shows just the contribution of the pole. This shows just the contribution of the zero. For example, here you can see that when the angle is 0, the length is 0.5. And as the angle goes towards pi, the length of the line goes to 1.5, 1.5. And finally, you can show the contributions of everything. Here's the pole, here's the zero. This is the constant k here, and the dotted line is the product of all of these traces. The little 0 button sets the angle of the bug back to 0. This program is one of a suite of programs that I have developed to explain DSP concepts to my students during lectures. There are now well over 24 programs covering many aspects of the material in the book, including complex exponentials and sinusoids, convolution, the DTFT, pole zero plots and their relation to frequency and impulse response, A to D and D to A conversion, including upsampling, downsampling, resampling, and aliasing, the design of many types of FIR filters and their application to the filtering of speech and other signals, the design of IIR filters, circular shift and convolution using the DFT, the discrete cosine transform, and the short-time Fourier transform. A selection of these programs is being made available to instructors who are currently adopting the book in their classrooms. For further information, please visit cambridge.org/Holton.